Hello. Okay, so let's begin, everyone. And this is the daily lecture summary for today. And I have, yes, so please pick up the lecture summary sheet. I have updated the list of active learning credits for meeting 36 to meeting 39, so please check. And I have a new customer, someone decided to fill out the midterm feedback. So I'd like to respond to this, and regarding the big picture, if you have any questions about the big picture that you didn't understand, feel free to ask, okay? Then you get active learning credit rather than just not saying anything. Because even if you mentioned in the feedback, I don't know what was the problem. And I just want to really specify what I did in the Beatles topics, and the goal, my goal at that time, okay, when I started the Beatles topic, actually on the spreadsheet, was really to provide the class with the solution guide to solve problem 4.7. And that's why I had to present the topic in that order. The goal was really to train you or to explain to you the spreadsheet for music note detection. So I did not start the Beatles topic with the first section, okay? And the first section would be section 25C, right? And but I started with something. Well, maybe I want to go back to this, so I don't want to move this part here, meeting 36. Okay, but we'll come back to that. I just want to explain to you why I started the topic, the Beatles topic, in that order instead of from the beginning, and it was really to train you to do problem 4.7, okay, just like I did in previous lectures. And I mentioned to you that I will present the Beatles topic in the ASEE conference. It's probably in less than 2 weeks in Gainesville here. And this is the abstract. I'll let you read through the abstract, but this is from the American Society of Engineering Education. And I'm also preparing my talk slides right now, and I will use my talk slides to also present the topic to you and in a more condensed form. So that will give you an even bigger picture. Okay, so we'll come to that. But for today's lecture is I'd like to go back to Fourier analysis, particularly Fourier series. As you see here, we have already talked about, at least at the end of section 9a, on the even and odd function, so you can do some of the problems in report 4. So now I'd like to address the Fourier series with additional street fighting examples, and I will go back and forth between the theory, the formulation, and the examples. Okay, so let's begin with the examples in section 9b, right? And then I will do something that is even more general than what you see in section 9b, because from what you already did with my lectures and with the report 4, this should not be too difficult. Okay, so let's and I'd like okay, I may need to go here and section 9b.
Could you scroll down to your remark about the street fighting series?
Sorry?
Could you go back to and scroll down to the remark about the street where it says remark?
Yeah.
Transformation. No, down one more where it says remark street fighting series.
You mean, oh, I'm not
okay.
there yet. Yeah, so don't jump ahead. Yeah, I'd like to present in order, and so as you know, every day I start with a daily lecture summary and I go down in order like that, okay? So it's always like that, very structured. So if you follow my daily lecture summary every day as advised since the beginning of the semester, you would not be overwhelmed by the information. Otherwise, it can be scary, okay? All right. So this is section 9b. Let me present in two small windows so you see where I'm heading to, and then I'll zoom in with a middle window. Okay, so first, so everyone would see that this is section 9b, and for those of you who want to see the big picture is always in my daily lecture summary, and it's also encoded in the in the table of contents at the beginning of each section, okay, as shown here. All right, so that's the big picture, and so in this particular lecture today, we go directly into the street fighting example, another street fighting example you saw already before regarding the parabola. So now let me remind you, one more reminder or review if you like, is that to do Fourier series in a way, this is all you need. These are the formulas that you would need to expand into Fourier series. How to derive these formulas is a higher level, okay? But to apply these formulas, it's just a matter of doing integration, okay? As you have seen already, and so we'll come back to the derivation and connection to projection. So this is another big picture here. You have seen the graph matrix, and I have mentioned to you the parallelism between functions and vectors, right? In vectors, you have Cartesian coordinate system, you have oblique coordinate system. In functions, you would have, for the equivalent of the Cartesian coordinate system, that would be the Fourier basis function, because they are orthogonal to each other. And for the oblique coordinates, that would be the polynomial basis function. So vectors and functions are completely parallel, okay? They cannot be viewed as, or it is wise not to look at functions as completely separated from vectors. That would be a mistake. Because you are used to functions for many semesters or many years ago, so you can build on top of your intuition that you have with vectors and generalize to functions. That's the most powerful way to think. Okay. If you are disconnected from vectors, then this would be too abstract and could be difficult. Okay, so let's look at the first example, very simple example. It's even simpler than the parabola that you saw in my lectures and that you had the chance to apply in report 4, but it will get complicated soon, okay, very soon. So like I said, it's just a matter of applying these formulas to, so this is a Fourier series, okay, and the function f is given, and so what you need is to compute the coefficients, right, a0, an, and bn, using these integral, okay. And so for the example, that's a rectangular wave or square wave, and as indicated by the figures, right? So the figure is self-explanatory. It's periodic. You can consider the period as going from minus pi to pi, right? So this would be equal to minus L here, and pi would be cap L, and 2L would be 2 pi. So you can view one period as shown in this circle. Okay. And mathematically, well, you know, this is what is described mathematically. It's good to walk you through this so that you are at least used to the notation of the language. So this is the case where the origin of the period is at the center, right? So the origin is at the center of the interval from -1 to +1. And so the period is going from minus pi to pi in this example, and the function is described as having the value minus k if x is between minus pi and 0. So this is minus k here. Think of k as a positive constant. And the function f is equal to k for x between 0 and pi, right? So that's, you have the blue line up there. So that's one period. And for periodicity, this is the description, meaning the function f at x plus 2 pi equal to the value of f at x, okay? Where 2 pi represents the period. So if you keep moving, adding a number of periods, you get the same function. Actually, more general than this, you can write, let me perhaps write in my notes so that you have something that you can keep, or you know, it's posted. So another way that you can write is as follows. For a periodic, or another characteristic of a periodic function is that f of x plus np equal to f of x, okay? Where n would be any integer. So that means that if you add any number of periods, right, translating any number of periods, n can be 2, 3, 100, 1 million, you get the same value, okay? So it's not just one period, no, n period. Okay, so that, and I'll come back to the case where the origin is at the, oh, maybe I can do that too. It's not so bad. You know, another way to see a periodic function is that you look at this interval here, where the origin is on the left, right, of the interval, and this is a period here, p equal to 2l, okay? And so 2 pi is 2l, right? So so the origin is on the left of the period, right? So, and here the value of the function would be equal to plus k when x is between 0 and pi is half the period. And the value of the function would be minus k when x is between pi and 2 pi, right? So this is another way that you can describe periodic function, and there's certain advantage to this picture that you will see. For as a characteristic or property of a periodic function, again, it's very similar. This is a mathematical way that you say that the function f is periodic. And as a street fighting method, you know, all you need to look at is this picture here, is this graph, okay? So the goal is to, let me zoom out so you see the big picture, and the goal is to expand into Fourier series. When you see here and zoom back in. This means section 9, page 6, okay? Now, A0 is 0. Let me zoom out and go up so that you can have both the figure of the function and this coefficient here in view. What would be the street fighting method to arrive at this conclusion immediately without carrying out the integration? Active learning credit. While I pick up my list, please think about this and discuss with your teammates if necessary and participate, to get active learning credits. Remember, active learning credits, worth each active learning credit I will add on top of the of your final course grade, so that may bump you up even one letter grade, But the grade is just a way to motivate, I hope that you derive satisfaction from learning, from understanding, rather than just grade. So we have Maria, we have, is it Black?
Yeah.
Okay, so I got it finally, right?
Perfect.
Anyone else? Okay, so let's start with Maria and then Black.
Is it because the function's not continuous? Because with a Fourier series, isn't it a cosine? Or
Yeah, Fourier is cosine, so is it continuous or not continuous?
AO.
Cosine is continuous or not continuous? Yeah, you said correctly that Maria said that this function is discontinuous. Very good. This is clearly, and we will get to something about this soon. Something that relates Fourier series to discontinuous function. Very important property. But here, recall that I'm asking to justify why the coefficient A0 is equal to 0. So Maria, do you have anything more to add? I know Colton, but let's have Blake speak up and then Colton.
So if we're integrating from negative pi to pi, you can see that the values on the left is 0, we're gonna completely cancel out the values right under the
Okay, Colton.
I was just going to say that it's centered around 0, so the average value is always going to be 0.
Yeah, so in a way, you can think of this as an odd function. So basically, Blake and Colton essentially said similar things. So let me zoom out a little. Yeah, so if you look at this portion here, this function here is an odd function, right? It's anti-symmetric about the center 0, and this area is negative and cancel out exactly this area. And but Blake and Colton, let me ask you, can you remind the class, okay, the meaning of A0? This is very important. The meaning of A0, because that's a street fighting method. When you talk about integration, yeah, that's mathematical, There's something that is more fundamental than that. Nick?
Is A0's the average value? So
The average. Okay, so very good. So if you look at this period here, from minus pi to pi, the average of this function is 0. That's it. Okay, and that's the physical meaning of A0. So I have Maria. Maria is teammate. This is meeting 40. I have Blake is team 3, and Colton is team 2, and we have Nick is team 7. Yeah. Okay. All right. So. And the street fighting method is just to have a quick way to verify, an intuitive way to verify. But of course, you need to know how to do integration. Okay. So the next step is to find the coefficients, and so here is the coefficient for an, and these are very simple. This is much simpler than the parabola, so I'm not staying too long on this. Okay, now you see that first a sub n is 1 over L, and L is pi, right? That's half the period, and integral from minus L to L of fx times cosine n omega x. Question. Where is omega?
Omega is 2.
Remember, omega is a circular frequency of vibration or angular velocity, and you can relate omega to the period, right? So why is omega? Where is omega? So we have Brennan. Anyone else? You know, if you cannot write this expression, you cannot integrate, right? There's nothing to integrate. So if you cannot even start to write the expression for an, there's nothing more to say. So anyone?
Isn't
Yes.
omega canceled out if it's like if it turns cosine into 1?
Turn cosine into 1, okay.
Or-
Remember the formula. Let me remind you the formula. Okay, so
What was the formula for
okay,
omega?
so the formula that you would have in your formula sheet, if you go into the exam, but you know, exam is the lowest level of motivation,
There it is.
right? You want to learn to understand. So let me zoom in so that you can see that this is the formula. I'll come to you, Brennan. This is the formula for an here, see? And you see that the coefficient or the factor that you have to multiply by f, the function f, is cosine n omega. You know, note that here there are two formulas, right? Okay, one formula goes from 0 to p or to L, and the other is integration from minus L to L. Okay, so we have Brennan, we have Devan, and we have Kyle. Let's start with Brennan.
Omega is 2 pi over p, so p is 2 pi, and omega is 2 pi over 2 pi, so omega is 1.
Okay, how about Devan? Agree, Kyle? Okay, so yeah. So what Brennan was saying is that because of this problem here, you can see the picture here, the period p is equal to 2 pi, and omega, right? Omega, let me write over here, omega is equal to 2 pi over p, and I showed you a street fighting method to remember this formula. Okay, I will not go back to that. Please watch the video if you forget. And so therefore this is what Brennan said, and we have the agreement of Devan and Kyle. Okay, so let me note down. Brennan is, while I'm doing this, if you don't remember how to rederive the formula, omega equal to 2 pi over p, please review that. I just take a few seconds here to note down the name. We have Brennan is team, what team number? Oh, team 3. The line is team 6. And Kyle is team 6. Okay. Very good. Alright. So every detail must be explained. You know, do not memorize. So, okay. Next question, very quick. Street fighting method. Takes a long time to, it takes some time, not too long. It is a very simple integration. Is there a way that you can arrive immediately at this result without integrating, without doing all of this work? This is a review for the exam, by the way. Okay, we went through this several times already. So we have Devan. Anyone else? Remember here, if you can answer the question, please participate, get active learning credits, and we can move forward. Okay. And if you cannot answer the question, well, you know, you have not actually mastered the material. Anyone other than Devang? Okay, the man.
Since cosine is an even function and f of x is an odd function,
Yes.
when they're multiplied together, you
Right.
have an odd function, and then taking the integral of the odd function
Yes.
would result in 0.
Right. You know, so for this problem here, the function, maybe I should show to you the function right here. Yeah, I just said that it was, you know, if you look at this interval here, it's an odd function, it's anti-symmetric about the origin 0. So therefore, f is odd, cosine is even, and the integration is from minus pi to pi, you know, centered over the period. So therefore, the result of the integration is immediately 0, right? So, but you need to write all of these arguments if you don't want to carry out the integration, okay? All right, so therefore, what is left is only to do to find the value for the coefficient Bn, right? So therefore, the Fourier series for this square wave with the origin as shown there would be a sine series, okay? Because it corresponds to an odd function. Okay, so therefore the sine series and the coefficient Bn would not be equal to 0. And so this integration is simple because the value of the function is constant, right? So it's very simple, easier than the parabola that you did, so we're not going to go through the details. And I just want to show to you the result. The result is right here. Okay, of the integration. So let me keep the integral of Bn and go through slowly, right? So this is the result of the integration, and then with some additional you know, particular values depending on the value of n. Remember, n is also the summation index for the Fourier series. And so, for example, this is n equal to 1, and then n equal 2, n equal 3. You know, it's a pedestrian method to explain as in the book. Then you have the value of B1, B2, B3, B4, B5, and so on and so forth, right? So what you notice is that when the index n is even, then the coefficient B would be 0, right? When n is an even number, so B2, B4, B6, and so on and so forth. But you know, when you do like this, it's not convenient to plot and to see the convergence, right? So you want to have a compact formula, and that is right here, what the book does not tell you. And so I have here provided to you, you know, so this is what the book gives you, right? Crazy, or any other book. Or you can rewrite yourself. This is so simple that there's no need for any book. But you know, writing like this is not so convenient and useful, because what if you need 100 terms, right? You write 100 terms, that's too much. But if you write this series in a compact formula like this, you can code into decimals and you can view the convergence, and this is what I'm going to show. Okay. So and so let me remove this. Just show to you a few a few a few plots of the truncated Fourier series. So for example, here you have okay, S is mnemonic for series. So S1 is when you have only one term, you know, from this series. S2 would be when you have two terms. And so here you have the plot of S1, S2. You know, S1, essentially you can sort of see that it's an odd function. This is the function, you know, the value of the function which is constant. But when you increase two terms, you see that there's a better approximation, right, of this stat function, discontinuous, like what Maria was saying. And let's continue on. And then if you have three terms, then you have better approximation, right? S3 would be the blue curve here, and S2 would be the dotted line. Okay, so let's look at the animation that I created. And I should have it here, I think. All right, let me use the projector mode so you can see the line darker. And let me walk you through slowly. Okay, let me turn off this sine series and zoom out. Oh, something happening. Yes, Maria.
Why would the Fourier series be appropriate to approximate a discontinuous
Very
function
good.
like that?
Very good. Excellent question. So Maria, let me repeat the question so that it's recorded and everyone can hear. You know, Maria said, well, this is a discontinuous function. How could you use, sorry, I don't mean to increase like that. I mean to zoom in like that. You know, it's a discontinuous function. Oh, by the way, what is a discontinuous function? How do you define a discontinuous function? What's a strict fighting definition of a discontinuous function? Maria?
There's two, what is it, that there's two definitions to X?
Two different values
Two different
at a
values.
point.
At a
Okay,
point.
so for example,
At
if you
X
look at
equals
this,
0, there's two
yeah, if you look at
Ys.
this point, and if you approach this point from the left, you have one value. If you approach it from the right, you have a different value. And infinitesimally small, and then you have two different values at the point. Okay, that's the mathematical description of a discontinuous function. And the question that Maria asked was, okay, how can you approximate a discontinuous function by continuous function? That's a very deep question. Okay, please keep that in mind. We'll come to something that is called the Gibbs phenomenon. And Gibbs was considered as one of the founders of the field of thermodynamics. Okay, a very, I mean, in itself is a very abstract field. Talking about thermodynamics, I could not help to tell you a quotation. Maybe, you know, by a physicist. Let's see. Oh, I'll find it. I'll talk to you next time. Let me continue here. So let's see if I turn on this sine curve and increase j. You know, so basically you just see an increase in the frequency. Okay, yeah, maybe what I want to mention to you before Maria asked the question is that, you know, this is not extended to from minus infinity to plus infinity. Okay, that's what you want to keep in mind, because at this time I don't know how to plot this square wave that goes from minus infinity to plus infinity. So all I did is I just have to plot each segment, you know, one at a time, and then I just want to plot a representative number of segments without plotting everything. Okay. Okay, that's too much work. So that's why you see that this function here, you didn't see anything here, but in principle, it should extend from minus infinity to plus infinity. And later on, I will show you a method that I discovered, and it will give you a plot of the square wave from minus infinity to plus infinity. Okay. The next thing is, let me show you the series. Okay, let's see here. Yeah, so this is the sine series here. So when I turn on the sine series, and this is the number of terms, okay? Let me move down, okay, right here. And let me zoom in into one period. So here, let's see. Yeah, so in this series here, I wrote a little differently. I wrote the sine series I have here 2m minus 1 and down here the factor 2m minus 1. So when m is equal to 0, you actually the value of the denominator is actually w or omega. At the time, I did not know how to write Greek letters on decimals, but later I discovered that, so I used w for omega. Okay, so when m equal to 0, you have sine of omega x. Okay, so so the number of term is small m plus 1, if you like. Okay, so this is the sine. So when cap m equal to 0, that's like I said, cap m plus 1 is the number of terms. So now let's increase the terms. You see, so here you have 5 terms, right? So when you increase, you see more and more closer and closer approximation. All right. Now watch the point of discontinuity that Maria asked, and watch what this Fourier series do. Okay. Now let me increase. I have 100 terms. Here you see, look, increase, 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 increase to 100, and you see that. And let me zoom in. Let me zoom in, and zoom in more, and zoom in more. Do you have convergence? Do we have convergence at the points of discontinuity? No. You have a phenomenon that is the oscillation here, and that's named after Gibbs. Like I said, many consider Gibbs as the founder of thermodynamics. But actually, this phenomenon was discovered by another mathematician, published before Gibbs. But Gibbs got the credit. In life, sometimes it's like that. The credit was not given to the original discoverer, but to somebody later. Jackie.
The real signals don't cut off.
The real signal?
A real signal doesn't ever have that sharp of a break. So
A real signal, yeah, okay.
What about?
But
for the Fourier series,
yeah, can you think of any real world application where you have a discontinuity?
the Eagle
That's-
light switch.
Real signal. If you look closer and closer and refine the time scale, you may be able to see something, but there's always a jump, right? Shock wave, or if you take a hammer and hit a structure, set it into vibration, that can be that is a discontinuous phenomenon. Okay, so discontinuity. Yeah, maybe like Jackie said, sometimes if you refine the time scale enough, you may see perhaps continuity, but that is too microscopic. Sometimes you really need to model more macroscopically, and you need to be able to describe discontinuous phenomena. Okay, so And later on, I will show to you that Fourier series. Oh, by the way, this is another real-world application here, and big picture. So, you know, it's not just this. The camera that you use every day, your smartphone. You know, the JPEG format is based on the Fourier cosine series. Okay, we'll get there later. But here, yeah. So, to answer Maria's question. No, you cannot use in reality, continuous functions to approximate discontinuous functions. You always encounter this phenomenon called Gibbs phenomenon.
Which is that it doesn't converge.
Yeah, you know, you cannot really obtain convergence at the point of discontinuity. But on the other hand, you see that you have been able to transform something that cannot be described by analytic function. And why do you want to describe the square wave by something that is analytical? Remember the big picture again? The motivation of why we got into Fourier series? Anyone? For active learning credit?
Because it's an approximation versus something going on legitimately.
Because it's approximation,
So you
okay.
can do like n equals 100 exactly. You know how to
M
really
equal
get an
100, you can
approximation.
M equal 1 million, you know. But what's the motivation of describing something like this, or periodic function in general, by the sine series? This I had motivated before. I had given the big picture before. Okay. What if you excite a second order differential equation, which describes many physical phenomena, right, by the square wave? How do you solve it? You have no tools from differential equation to solve it until now. And what's the method? Can someone remind the method? Suppose that you put the square wave and excite not just single degree freedom system. You can excite this with the 2 degrees of freedom system or 100 degrees of freedom system. And you can solve the system analytically. What's the method? Can someone remind the big picture for the class? And let me give Jackie the active learning credit while you think. So you see, I talk a lot about the big picture. And if you don't get the big picture, do ask again and again and again. Okay, it's not like that's the lack of big picture. Well, the way you solve it is by superposition. You can solve by exciting the system by each of the sine function. And you know how to solve for the particular solution of a linear second order differential equation when excited by a sine function. What would be the trial solution? By the way, this is a review for the exam here. Okay, we start to review very early. I already distributed the exam statement, so please.
Would it be
Maria.
the yp is equal to m cosine, or it was the m and the n one, right?
Yeah, so, you know, so this is a sine series, right? You have many sine terms. If you pick out one sine term, one sine function, and you use that as the excitation to a second order differential equation, right? You need to find the homogeneous solution and you need to find the particular solution. Homogeneous solution is simple, that's known. You know, that's when the right hand side is equal to 0. Particular solution is when the right hand side is equal to a sine function. What would be the trial particular solution? Like anyone else? Sorry?
Don't you use sine times cosine?
Uh,
Or sine plus cosine?
Sine plus cosine. Well, A times cosine something plus B times cosine something. You need to have 2 free parameters, right? And these 2 free parameters, because the reason is because when you differentiate a sine, you get a cosine, and when you differentiate a second time, you get the sine. So you need to have both. So you have 2 equations for 2 unknowns. Okay, so that's the big picture review there. But let me show you something that is related to section 9A, and which you before that, let me show you this. So let me go back to a smaller number of terms here, and let me do something that you would see that my code is valid for any period. Yeah, thank you, Casey. Okay, so you can change the period here. You see that the Fourier series follow the change of the period, right? And that means that the series is correct, at least for this test. Okay, and I can also change the amplitude, and you see that the amplitude of the Fourier series or truncated Fourier series follow the change in the amplitude. That's another test that indicates that the Fourier series is correct. So this tool here, Desmos, is very useful to test whether your Fourier series was correct or not. You can change your parameters. Okay, and I don't think I have enough time for showing you something more advanced, so I'm asking you to write the lecture summary. Yes.
When we are doing this rectangular wave, I don't know much about music, but whenever you bring a chord, you're essentially creating, you're stopping it and changing back to be represented by the discontinuous one and
You mean like playing a guitar, like striking a guitar?
which is why you can use Fourier series, not just for the notes, but because the you play guitar, it's not periodic at all.
Yeah.
It's like it's a